Section 3.4. The variation of enthalpy with temperature, a constant pressure. The definition of enthalpy is this equation. H is defined to be U plus PV. In an isobaric process, pressure is constant. Delta H is equal to delta U plus delta PV. Delta PV is just P delta V because P is constant. And then delta U is Q plus W. This Q is now Q sub P for the isobaric process. What about work? Work is negative P delta V. This negative and positive P delta V cancel. Now we have delta H is Q sub P. So in an isobaric process, the amount of heat is delta H. H is a state function, and therefore the H is an exact differential. So dH is the sum of delta H over delta T times dt and delta H over delta P times dP. Imagine we design a two-step process when the state of the system changes. The first step, we hold pressure constant and allow temperature to change. In the second step, we hold the temperature constant and allow the pressure to change. So this is the enthalpy change of step 1. This is the enthalpy change of step 2. And therefore, when the state of the system changes, if both T and P change, and then dH is the sum of the enthalpy change in the isobaric step 1 and isothermal step 2. How about volume? Does enthalpy depend on volume? Yes, but this expression includes the variation of enthalpy with volume already, because volume is a function of temperature and pressure. Now this part is simply delta H over delta T on a constant pressure condition is simply Cp. So this is convenient to express enthalpy as a function of temperature and pressure. We can also express enthalpy as a function of temperature and volume, or pressure and volume. It's just not very convenient. Now this part, how does enthalpy depend on pressure? After chapter 6, we can prove this part is V minus T times delta V over delta T in an isobaric condition. In summary, enthalpy depends mostly on temperature. For ideal gases, we can prove this part is simply 0 because delta V over delta T is nR over P for an ideal gas. T times nR over P is going to be just volume. Volume minus volume is 0. So this part is 0. For real gases, this part can be proven to be small. So enthalpy does depend mostly on temperature. For liquids and solids, this part usually is approximately just the volume, because the volume of liquid and solids do not change significantly when one changes the temperature. So this part is actually simply V times beta, and beta is the isobaric thermal expansion. Right? So again, this part is approximately the volume of the liquid and solid, because the volume of a liquid and solid is usually small. Therefore, the second term, this term, the dependence of enthalpy on pressure, is smaller than this term. Again, for ideal gases, enthalpy does not depend on pressure at all. For real gases, enthalpy does depend on pressure, but it's small. For liquids and solids, enthalpy also depends on pressure. The dependence is roughly the volume of the liquid or solid. That's usually pretty small, especially if you compare the volume of a liquid or solid with the volume of a gas. Now let's look at one numerical example. Let's calculate the enthalpy change of 1 mole water with a Cp of 75 joule per K. It undergoes the changes from 300 K and 1 bar to 310 K and 2 bars. So the temperature increase is 10 K. The pressure increase is 1 bar. So let's integrate Cp dt. That's how enthalpy changes with temperature. It's Cp times the temperature change. We get 754 joules. What about the enthalpy change? That's due to the pressure change. Well, we just need to integrate this part. The result is only 1.8 joule. You can see this number is much smaller than this number. So the enthalpy change depends mostly on the temperature for liquids and solids.